Welcome to the Pencast video of exercise 12 of the module Spectrum and Fourier series. A periodic signal x of t with a period t0 is equal to 4 is described over one period, so from 0 to 4, by the equation x of t is equal to 2 from 0 to 2, or x of t is equal to 0 from 2 to 4. For exercise A, sketch periodic function x of t for t on the domain from -4 to 8. So we are given already the function x of t on the domain from 0 to 4. So let's just simply draw that. So it is 2 from 0 to 2, and it is 0 from 2 to 4. Since the signal is periodic and we are given one period, so from 0 to 4 is one period with time t0, which is equal to 4. After this time, this signal simply repeats itself. So from 4 to 8, we would have a similar signal, where the first 2 seconds is of value 2, and the last 2 seconds is of value 0. And the same holds from -4 to 0. However, keep in mind that it has to be low, of course, from -2 to 0 to get this repeating pattern. For exercise B, determine the DC coefficient alpha 0 of the Fourier series. So our DC coefficient, what this actually means, A0 is our average value of the signal. So from the plot, we can already determine that our average value should of course be 1. However, we need to formally calculate it. So A's alpha 0 is equal to, if we take the integral from 0 to t0, so if we take the integral over one period of the signal of x of t dt, and we divide that by the length of that period, we will simply get the average value. Since we have a discrete signal, we have to split this integral. So we have 1 over t, t0, over the integral from 0 to 2. And in that part, the value of the signal is 2 dt, plus the integral from 2 to 4, where the value of this integral is equal to 0 dt. So as you can see, this integral simply vanishes, and we're left with this integral. So if we were to integrate, we would get 2 times t over 0 to 2. So we have 1 over 4 because the period is 4 long, and we have 2 times 2 minus 2 times 0, and we would simply get 1 over 4 times 4 is equal to 1. So that's a DC coefficient alpha 0. For exercise C, we have to use the Fourier analysis integral for k is unequal to 0 to find Fourier series coefficient alpha k. So the only thing we can actually do in this exercise is to fill in this integral. So our alpha k is equal to 1 over the period from the integral. However, we do not have a continuous signal, so this time we would again have to split this integral. From 0 to 2 is the first part, and in this case our signal has a value of 2, and let's fill in the rest of the integral dt, and again a second integral is equal to 0, so that one vanishes. So if we would have to determine the primitive function, we would have 2 times a correction factor. The correction factor is equal to 1 over the part in front of the t, so 1 over minus j 2 pi f0 k. And the rest of the primitive function is simply e to the power minus j 2 pi f0 k of t, which we have to integrate from 0 to 2. The first part, these are all constants, so we can take these out and simplify these first. What we already know is our f0 is 1 divided by the period. So f0 times the period should be equal to 1 if we would rewrite this equation. What do we know more? 1 over minus j we can multiply with j over j, which is equal to j, and j can also be rewritten as e to the power j pi over 2. So let's simplify this a little bit further. So these 2's would cancel out, the minus j would become a j, or an e to the power j pi over 2. Our f0 and t0 would be equal to 1, so those two would also vanish. So what we would be left off with is 1 over pi times k e to the power j pi over 2. And then the part we have to integrate over. So f0 kt from 0 to 2. So if you now were to fill these values in, 1 over pi k e to the power j pi over 2, you would end up with, if we would fill in the value of 2 for t, we would have 4 pi k minus j 4 pi k times our fundamental frequency, which is 1 over 4, so these would cancel each other out. We will be left off with 1 over minus j pi k minus e to the power, if we would fill in the 0, you would get e to the power 0, which is simply equal to 1. So this is equal to 1 divided by pi k e to the power j pi over 2. Keep in mind that e to the power minus j pi k can also be rewritten as e to the power minus j pi to the power k. And this part is simply equal to minus 1. So what we have is minus 1 to the power k. So we have minus 1 to the power k minus 1. So this is already an expression for our alpha k. In the case that k is even, we would get that our minus 1 to the power k, so for example to the power 2, would be positive. And then we have 1 minus 1, which is equal to 0. So in the case for k is even, our alpha k is equal to 0. In the case that our k is odd, then we would, for example, have minus 1 to the power 1, which is equal to minus 1. We would have in this expression minus 1, so minus 2. And then we would end up with minus 2 pi over k of k e to the power j pi over 2. We could get rid of this minus sign, since minus 1 is equal to minus j pi, or e to the power minus j pi, 2 pi over k e to the power j pi over 2, which would give us 2 divided by pi k e to the power minus j pi over 2. For exercise D, this periodic signal x of t can be expressed with a Fourier series. In practice, we approximate such a periodic signal with a finite number of harmonics. Make a sketch of the approximated version of x of t for n is equal to 1, showing that this approximation with one harmonic is a reasonable approximation of x of t. So what we will do is we will approximate x of t with the approximated function, so x hat t, for n is equal to 1. So we have, if n is equal to 1, we have k is equal to -1, 0 and 1. So we have to keep these three values in mind. If we had look at things we calculated before, we know that our alpha k for k is equal to -1 is equal to 2 minus 2 of pi e to the power minus j pi over 2. And as we have already seen before, e to the power j pi is equal to -1. So we can write this as 2 over pi e to the power j pi over 2. Our alpha 0 was our dc, which was equal to 1, and our alpha 1 is equal to 2 of pi e to the power j pi over 2. So let's simply fill in this summation. Let's start off with k is equal to -1. So what we get is 2 over pi e to the power j pi over 2 multiplied with e to the power j. Keep in mind again that f0 is equal to 1/4, and in case k is equal to -1, so this would lead to minus j pi over 2 times t. In this case, for k is equal to 0, we would have a 0 in the power, so this e to the power 0 would be equal to 1, so we'd be left with a dc, so that's equal to 1, plus, for the case k is equal to 1, we have 2 over pi e to the power minus j pi over 2 e to the power j pi over 2 t. If we now were to rewrite these exponential functions, we will get something that should be a little bit familiar. So let's take the 2 divided by pi out of brackets, and you would end up with e to the power j pi over 2t minus pi over 2 plus, and that was this part. And then now I'll rewrite the first part, e to the power minus j pi over 2 t minus pi over 2. So this should become a little bit familiar because this is also an expression of a cosine. So if we were to rewrite this, we get 1 plus 2 over 4 times the cosine of pi over 2 times t minus pi over 2. And you should also know that if a cosine has a phase of minus pi over 2, you can rewrite this as a sine. So you get 1 plus 4 over pi times the sine of pi over 2t. So what we're left to do is to simply draw this in the figure we have already drawn before. So this value is approximately equal to 1.3. And we know that we would have 0 crossings. If t is equal to 0, t is equal to, so sinus of pi, so t is equal to pi, and t is equal to 4. The maximum would be at t is equal to 1 is the max, and the minimum would be at t is equal to 3, where it has a minimum. So, if we were to draw the signal, so let's go to the plot we had drawn before. We would start off at 1. We would go to 1.3, 2.3, down again, etc., etc. So this would approximately be our signal. So this sign is an approximated version of the block wave that's described here. So for exercise E, now we replace this periodic signal x of t with another related periodic signal y of t, which is defined as we can see here. So with a different amplitude, phase shift, and some kind of offset. Since y of t is again periodic with the same period t0, we can write it as the following Fourier series, which is given below, which is almost the same as we had right here. However, we now have a beta k instead of an alpha k. How are the Fourier series coefficients beta k of signal y of t related to the Fourier coefficients alpha k of the signal x of t? So what we can do is we can rewrite the function of y of t, which is given here. However, instead of filling in x of t, we fill in its Fourier series. So what we get is the summation from k is minus infinity to infinity of alpha k e to the power j 2 pi f0 k times t. However, instead of t, we now have t plus t0 divided by 2. Then of course minus 1. So we can split the powers of our exponential function. So and we can move the 2 between the brackets. So 2 alpha k e to the power j 2 pi f0 t0 divided by 2 k times e to the power j 2 pi f0 kt minus 1. We know that f0 times t0 is equal to 1, so those two cancel out. The same goes with the 2's, the factor 2 will also cancel out, and we will be left with summation of k is equal to minus infinity to infinity 2 times alpha k e to the power j pi k. However, we have already seen that this is equal to minus 1 to the power k, so minus 1 to the power k e to the power j 2 pi f0 kt minus 1. If we now have a look at the Fourier series of y of t, we can simply see the value of beta k. Beta k is related to alpha k using the following expression, 2 times alpha k minus 1 to the power k. Simply have a look at these expressions. However, this is only for the case that k is not equal to 0. For the case that k is equal to 0, we can see that in our signal, our DC is shifted 1 down and the amplitude is doubled. So in the case for beta 0, it should be equal to 2 times alpha 0 minus 1.